Everybody, this is Austin Hoggett here to give you another lecture from OpenStax Intermediate Algebra. Today we're going to be talking about roots and radicals. This chapter starts with an explanation of the definition of the radical. We'll look at some numeric expressions and ask how do we simplify the root. We'll also introduce how to do the same with variable expressions. In the next section, we'll look at some more interesting cases. For now, we'll open the toolkit with the basic definition. So how do I simplify some expression with a radical? The connection here between roots and exponentiation is important. We actually identify the definition of how to find the root with the connection in mind. So here we use the definition of taking the square of a number. If I multiply some integer or numeric value by itself, I get a new value. I can find what's called the square root by using the symbol, the root symbol, and the connection. So notice the definitions here are sort of synchronized. If there's some number I can multiply by itself to get a new value, we call m, then taking the square root of m is how we find the original value that we multiplied by itself in the first place. So I'll actually utilize this definition a great deal when trying to simplify a radical. Another idea to think about here is what the sort of nomenclature is. The radical sign itself can have what we call different indexes. In other words, we can take other things than the square root. We can take the cube root or fourth or fifth root of some expression. The expression itself that we're taking the root of is referred to as the radicand. And I'll come back to that idea a little bit later and how it's useful. For right now, let's take a look at sort of a connection between some geometry and taking the square root. Imagine for a moment if I have sort of a mystery block and I ask that you find the side lengths of this particular figure. And I'll go ahead and tell you that the figure itself is just a square. And so, for instance, here, if I said the area under the sort of block, or inside the block rather, is 100. So what are the lengths of its sides? That is, in definition, how we ascribe finding the root of this particular geometric figure. So the lengths of the side are going to be 10, because that's what we would multiply together to get an area of 100. So it must be then that the square root of 100 is 10. So partly that's an answer to our question here. What are the side lengths? But we could also answer this a different way. We could also imagine that in a different part of our sort of plane here, that we are asked a similar question with the same figure. So here I have a block now of 100 still in area, but the side lengths would actually be negative 10. If you can imagine again that this is in the x and y plane, it stands to reason that really there's two solutions to the question of what's the square root. In fact, that's exactly what we identify when we ask what is the square root of numeric value. We can also use our definition that we pointed out a second ago to sort of reaffirm this. So the way that we would phrase this using our definition is to pose the question, what value, when multiplied by itself, gives me back what's under the radical? Partly it's helpful to think about this process with some of our exponent rules in mind. So one of those exponent rules says that if I can multiply a number by itself, then that value must be a perfect square. For instance, here I can think of 100 as 10 times 10, either by factoring or prime factorization. Now, you may be able to easily recognize 100 as a perfect square, meaning the same base gets multiplied by itself to get that value, and easily identify, therefore, the square root. But not always is it going to be that easy. So one thing to keep in mind is that prime factorization, or the ability to break a number down, becomes really handy when trying to simplify roots. We'll look at some more advanced techniques for how to use that a little bit later. So as well as 10 multiplied by itself giving me 100, we said that we could also say, well, negative 10 answers the same question. The two negative signs happen to cancel out, And so, yes, we do end up with two solutions using either the visual geometric figure or our definition of the root. By the same sort of thinking, we can answer that the square root of 16 must be plus or minus 4. Generally speaking, when we ask what is the square root of some number, we really only care about something called the principal root. So in the case where we're talking about the principal root, we really are only talking about the positive answer to that question. So principal and positive may help you make that connection a little bit easier. So typically when you see questions like these, what's the square root of 100? It won't give you this plus or minus 10. It will just say positive 10, with the implication being that your answer is the principal root. Let's look at a few more questions here. Let's actually start with part B. Again, I could look at this using my definition of the root. What value raised to the second power is going to give me back 81? And again, thinking about my factors of 81, it happens to be the case that I know 9 times 9 gets me to 81, which therefore answers the question, what value raised to the second power gets me back what's under the radical? Since I can answer that question easily, it must be the case that the square root of 81, at least the principal root, is positive 9. Similarly for part C, I can pose the question. However, it's phrased a little bit differently here since it's asking me what is the opposite of the square root of 25. Well, what value when raised to the second power gets me to 25? It happens to be 5 squared. So it must be the case then that the square root of 25 is, at least principally, positive 5. The opposite of that would be negative 5. So we get negative 5 for part C. The answer to part A becomes a little more interesting. I can pose the question, at least initially, the same way that we did before. What value when raised to the second power gets me back what's under the radical? The problem is I can't think of anything that answers this question. If I use, let's say, positive 2, I could get positive 4 back out, but negative 2 doesn't work either. Negative 2 times itself would give me positive 4 as well. So I'm kind of out of ideas. It turns out in this case that there is no real number that answers this question. But there is a solution. For a question like this, we're asked to find the square root of a negative value. We're actually going to end up with what's called an imaginary value. So the solution here is 2i, where we say that I, the imaginary unit, is defined by the square root of negative 1. We'll sort of show how we can identify where imaginary numbers show up another time, but be aware that we can take roots of negative numbers even if they're not real values. Let's take and expand on our definition of the root, though. I mentioned a little bit earlier that we can actually take the root of things other than just square root values. And so we can kind of generalize our definition that we used earlier. We said that if we can take some base value and raise it to the second power, and then square root the new number we create, we would find the original base. If we take any base and raise it to any integer to get a new value, we can work backwards then to find that original base using the same principle. So here they show us what's called the nth root of any value, and that's just a way to generalize this notation. The nth root in this case refers to the index of the radical that I'm trying to take. So our definition does not really change. It just sort of follows this index. Now there's some interesting properties here to note. For instance, it says when n, the index of the root, is even, and the number that we're trying to take the nth root of is positive, then that value is going to be real. It's going to be a real number. However, if we're trying to take the even index root of an expression that is negative, that is always going to result in an imaginary number or a not real number, as it's stated here. If n, the index of our root, happens to be odd, though, then we can always get a real number for the values of a. We'll see why this is in just a moment. So take a look at some examples here. We're asked to find the cube root, fourth root, and fifth root. So let's use our definition. Whereas before we were looking at square roots, for instance, in part A now we're looking for what raised not to the second power but to the third power will give me back what's under the radical. Now, when you get into these higher index roots, it can be a little bit more of a challenge to identify what the sort of factors are that go with this expression. So for instance here, I may start by either factoring 64 and trying to identify repeated factors. This could be done through a process of prime factorization or using our division rules. For instance, I know that 64 could be divided by 2 to get 2 times 32. And I could factor 32 to be, 16 times 2. And so, at least initially, I can see that there's 2 factors of 2. If I keep breaking the terms down here, 16 becomes factors of 4 and 2, or excuse me, 8 and 2. So let me clean that up a little bit and get to the point. The idea here is that if I have 1, 2, 3 factors that are the same, they create a perfect cube. And so identifying the perfect cube in the bunch here is a little bit more challenging. What you actually identify is that, if I continue to break the numbers down, we have 2 times 2 times 2 times 2 times 2 times 2. So I think those are all the factors. Again, we've got 3 identified, all multiplied by 8, and 8 breaks down into 3 more 2's. So what are my 3 numbers that I multiply together to get 64? Well, it's 4 to the third power. And so we would identify the base as being 4 through either prime factorization or just having seen these enough times to recognize how we get there. So sorry this was a little messy, but my process of prime factorization here will get me to an answer for a lot of problems. If I am looking for perfect squares, again, the idea is to just identify the number of factors that matches the index. So I had to have a 3 set of 4's to make a perfect cube in this case. So we can then say that the square root, or rather the cube root of 64 is 4, because that's what we raised to the third power to get back what's under the radical. For part B, we're asked to find the fourth root of 81. And again, if I go through the process of factoring, 81 is 9 times 9, but we're not looking for duplicates. We're looking for 4 pair of the same factors. So if I continue to factor, we identify 3 as the thing we raise to the fourth power to get back what's under the radical. And so that must give me the root. And lastly, for part C, we pose the same question. What raised to the fifth power gets me back what's under the radical? So in this case, we'd find that 2 is the value that we can multiply together 5 times to get 32. And so that gives me the fifth root in this case. So that basic definition of the root is useful in instances where we're looking at what's called a perfect term. 64 was capable of being written as 4 to the third power, and we were trying to find the cube root. And so the index and the exponent here match, canceling each other out, leaving me with just the base that I'm interested in. The same occurs for the other 2 examples here as well. So a couple more examples. Let's look at instances where we're finding the cube and fifth roots of negative numbers. Notice in the last few examples we showed, none of the answers happen to be imaginary values. And it's instances like this where I have a negative under the radical that I have to consider that maybe my answer is going to involve some imaginary value. It won't in this case, however, because of the sort of index for each of these roots. In the case we're looking at the cube root of negative 27. Again, the question posed is what value raised to the third power gets me back what's under the radical? So is it possible even to multiply something together 3 times and get a negative number? And the answer is yes, because there'll be an odd number of negative signs. I will actually still be able to end up with a negative value. So I can think of factors for negative 27. Ultimately, I'll come up with negative 3 to the third power is what would get me back to the original expression here. So it must be the case that the cube root of negative 27 is negative 3. Similar situation for part B. We already answered what raised to the fifth power gets me back what's under the radical in an example where we said, let's find the fifth root of positive 32. So we know that the base should be 2, but now it's going to be negative raised to the fifth power, which gives me, again, my solution here. The fifth root of negative 32 is just negative 2. So we looked at numeric values. Let's introduce variable expressions as well. For integers where we have something like square root of 2 or higher, we sort of break this into 2 parts. If it's even, we have to signify that our answer is positive using the absolute value. For instance, the fifth root of, the fourth root of 5 to the fourth simplifies to just give me the original base, 5. Notice that the fourth root of negative 5 to the fourth power gives me the same answer, even if the original expressions are different. And so we actually still end up with the absolute value, in this case, of our number. So it's not always going to be the case that when our index and exponent match, that they'll just cancel out and we're left with the base as is. We got to be cautious in cases where the index is either even or odd. Look at these 2 examples here. I've got one of each. In part A, we're looking at an instance of an even index. So we want to identify, again, what raised to the second power gets me back what's under the radical. And hopefully it's really obvious in this case that x is what we raise to the second power to get back what's under the radical. So it must be the case that the square root of x squared is just x. In part B, we've got a similar situation. The exponent and the index of my variable happen to match. So again, if I pose the question, what raised to the third power gives me back what's under the radical, it's pretty obvious. N is what we raised to the third power. So again, looking back here, we have to be cautious. When the index is even, we might have to signify that we're talking about a positive version of our base using these absolute value bars. And so technically speaking, we should say this is the absolute value of x. So on pencil and paper, this is not as critical of an idea. However, in WebAssign, you may find that you need to use the absolute values for solutions. Another couple examples here, we illustrate how to find the square root of a more complicated expression. Notice that I have both a variable term and a constant of some kind. So for instance, in part A, we would still pose the question using our definition. The only reason, though, is because everything can be written as something to the second power, which is nice. So how do I do it? Well, for instance, 16, we could rewrite as 4 times itself, or 4 squared. N squared, obviously, is already written as a square term. And what I can do now is reverse one of my properties of exponents and say that, well, if 2 terms are raised to the second power, I can raise them both to the second power if I put them in parentheses. And so I can signify that the square root of 16 into the second must be 4n, because those are the expressions, or rather 4n is the expression itself that I would raise to the second power to get back what's under the radical. Similarly for part B, although in this case it's a little bit different because they asked me what is the opposite of. I'll first start with my definition. What raised to the second power will give me back what's under the radical. And again, I'm reversing one of these definitions of the sort of exponent to work out the base itself. Non-c is what we raise to the second power to get back what's under the radical. So what is the opposite of the square root of 81c squared? Well, again, the square root of 81c squared would be non-c, but we want the opposite, so negative non-c. One last trick I want to show you before we finish here. In instances like this, we could still use our definition to answer the question. What raised to, in part A at least, to the third power gets me back what's under the radical? And in this case, again, we could use some of our exponent rules to work this expression out. We could say that y to the 18th could be broken up into 3 times 6. And again, reversing some of my exponent rules, we could say that y to the 6th is what we would raise to the third power to get back what's under the radical. And so that gives me my solution. There's actually another way to think about a problem type like this, however. Another way to think about the connection between roots and radicals is to understand even further the connection between exponents and roots. So another way to write roots and root notation is to take the base and raise it to a fractional exponent. The index of my root becomes the denominator. The value of my exponent becomes the numerator. Why this is handy is because instances where the exponent is divisible by the index will result immediately in the solution. So for instance, in part A, 18 is divisible by 3. We would be able to write it as 18 divided by 3, which gives me the solution, y to the 6th. Let's use this for my answer in part B. I'm asked to find the fourth root of z to the 8th power. I could go through the motions that we did in part A, reverse the sort of exponent. However, I could also just write it in this form, 8 over 4, which reduces to 2. And we would find just as well that the fourth root of z to the 8 must be z squared. So that works out really handily in some instances using exponents. Again, though, it's critical that your exponent is evenly divisible by the index. We'll talk about some situations where that's not the case in the next lecture.